Show them this one. Beat some of those Strava PBs. Sorry for the miscalculation of pizza. That won't happen again, I promise. We're going to make two apologies.
It's okay, you can't again.
Two apologies. Three. One, I made a mistake with pizza. In my talk, I'm talking, that's probably the second one. The third one, I'm going to show you a bit of .NET code. So some C#, so I apologise profusely for that. But that's something to look forward to. But until then, here's Squire, who can't get his laptop to work, so I question the quality of the talk.
I would too. You have C#, so I
think I lose. Yeah.
The glass houses and all that.
Yeah.
All right. Well, yes.
Yeah. There we go.
Okay. So last month, myself and Jan over there gave a talk at React Summit in Montreal, and I'm going to attempt to give the same talk in 15 minutes. What was originally a 30 minutes, 45 minutes talk. However, how do I go to?
Oh no, you're doing it in PDF. Just click expose, the green button in the top.
Oh yeah, that'll do. Right. So far, you're doubting whether I can actually operate computers, let alone program them.
We're in a black screen.
Now, in true lightning talk fashion, this was me an hour before arriving here. I was contemplating the title that I should click to add, and also eating a piece of cake. Nevertheless, a talk has emerged from it, so I'm going to tell you 6 lessons that we learned about distributed systems at scale, in production, within 15 minutes-ish. You don't care if it runs over because you've just eaten pizza and you're falling asleep anyway. So the what and the why. For the past year, we've been building at Disney Streaming Services a system that monitors and operates stream processing devices. So one of the things that we do is broadcast live sports events, for example, ESPN Plus in the United States. And to do that, we need to transcode the media, or we need to segment the media, and we need to do it in real time. So we have these processes that run in data centers in various parts of the world, and sometimes these processes break in various ways. They need to be reconfigured by human intervention when a new game is scheduled. So we built this system that kind of watches over those devices. We treat them like IoT-style devices, and we monitor them by shadowing them. And everything we do to these devices and everything that happens to these devices, we record into an event stream so that the rest of the business can see that information and make decisions based on it. So that entails exposing health checks, pipeline topology, providing a global view of the pipeline. Lesson 1. The distributed system without durable messaging easily grows into a monolith. So if you're deploying a distributed system that's made out of many microservices, you want those services to be loosely coupled. You don't want, like we build microservices in the first place in order to avoid having a monolith. But then there's a risk that your services make assumptions about each other when they communicate with each other. So if you, for example, were to say, well, everything will talk using REST. Now every service needs to know about every service's REST API that it wants to talk to. And if you change one REST API, you need to know what else to change elsewhere. What you really want is a decoupled messaging system, let's say Kafka. Doesn't actually matter, it could be Kinesis, something else, but we use Kafka. And you don't just want to use decoupled messaging, you also want those messages to be durable. So what that means is that after a microservice has acted on a message, it should still be possible to go back and act on that message again. We should be able to replay messages. Services should be able to go back in time. They should be able to consume messages at their own pace. So in order to do that, we need to persist messages. So we need them to be durable. That also allows us to be fault tolerant. So if a service crashes, comes back up, we can replay messages that it hasn't already processed. We built durable messaging in from the start, and we're glad we did, because when things went wrong, we were able to go back and look at the messages that had been processed. We could even write a test that replays the messages that we've seen in the past and find out how the system behaves in isolation in order to reproduce weird behavior that we've seen at scale. A distributed system without supervision is a binary thing. It either works or it's failed, and you can't inspect any more deeply into it to understand what's failed. So, what do we mean by supervision? Well, we mean that a process either is capable of dealing with an error when it occurs, or it's able to delegate dealing with that error up a supervision hierarchy to something else that can deal with it. So it might be that I can deal with a user with not being able to access a user database. I could retry. Maybe I retry twice. At some point, I have to give up retrying. At that point, that's when I have to delegate. I have to say, well, I've retried a couple of times to connect to this database. I can't do it, so I'm going to give up. I'm going to say throw an exception. Think of it like that. Exception handlers bubble up. Well, maybe my process gives up and dies, and now my orchestration system, let's say Kubernetes, has to find a strategy to deal with the problem instead. The advantage of having a supervision hierarchy is that things higher up from your process are aware of more information about the wider system, so they can make decisions that you can't make. So maybe the database is simply not available and you just scale down and wait, or you move processing to another AWS region. Maybe that's the strategy that you apply. A process in itself, like the JVM process, can't make that decision, but the provisioning system could make that decision. A distributed system without back pressure, it will either fail or it will make everything around it fail. So we can't just assume that your system will be able to process requests as they come in at any rate that they might come in. So maybe you have 1 request per second and you can handle that. But when it comes up to 10 requests per second, you can no longer deal with those 10 requests per second. You've got to think, what's the consequence when your process can't deal with 10 requests per second? What knock-on effects does that have to other processes around you? So, we get similar situations in, say, driving. If one person on the motorway decides for some reason they're going to drive at 40 miles an hour, they think they're safe. I'm driving 40 miles an hour, it's fine, right? But there's a knock-on effect because every vehicle behind them is having to slow down. And they're having to slow down more and more violently in order to deal with the emerging situation in front of them. So you're at the front of the queue, you think, oh, everything's fine, but somewhere at the back of the queue, someone's slamming the brakes on, trying to deal with the fact that all the traffic suddenly is slowing down. That's what we get in distributed systems if we haven't thought about back pressure. Your system fails, and now the system that talks to your system, that fails too, and it bubbles out, and everything fails. So, really, we have to start doing load testing quite early on in the process, and I'll talk about that a little bit more later. But that's how to know in advance, can you deal with back pressure? Because you can't just assume that you can deal with it. Observability and monitoring. So there's 2 concepts here that maybe we've made up a distinction here between observability and monitoring, I don't know. Excuse me. Observability is our ability to inspect the state of the system at any point that we like to do that. So if we look at, say, something in New Relic, or we look at a log aggregator, we're observing the state of the system. Maybe we even log into a box and interrogate the operating system, and that's an observation. Monitoring is something which is continuously happening. The application is telling you about itself. So an application could be telling you, I'm still alive, for example. It could be telling you how much memory is being consumed, how much CPU is being consumed, how quickly it's processing requests. And that could all be being pushed out to some external thing. Again, it could be relic, and that's where maybe this distinction starts to blur a little bit. I do have a picture, which is Andrew, so blame him. basically the idea is that we will have layers of observation and monitoring. So we have a JVM, and that's where our code lives. Inside there is an access system, so we can build instrumentation into that. And that allows us to observe how many accesses are in the system, how many messages are being processed by those accesses, and so forth. It also allows us to observe more fundamental things about the JVM, like memory use, CPU use, heat pressure. We can also, of course, collect logs as well. So these metrics that we get from the JVM and also from Akka, in combination with the logs, gives us observability. And then the JVM probably lives inside a container, which is orchestrated by something, let's say Kubernetes or something along those lines. We do monitoring on the container, so maybe we constantly hit the container to see is it still there. That's the orchestration system doing that. We could also be using the OS, right? So above the container there is an operating system as well. So we have similar monitoring from that. Look, that's not right. There we go. Distributed system without robust access control is a security incident waiting to happen. So it's all very well having a set of microservices that communicate using a message bus, let's say Kafka. But the trouble is, if service A is allowed to send a command to service B on a Kafka topic, that implies that anything can write to that Kafka topic, and service B will happily execute that command. We don't really want that, because that command might be delete users, or it might be download all of Disney content onto my USB stick and I'm going to take it home. Not only that, but once we start putting these controls in place, we can start thinking about ways to do very sophisticated load testing and chaos testing in a safe manner. What we'd like is if we're running a load test, for it to not do anything destructive. So we want to exercise all the different pathways in all the different services that we've deployed, but we don't actually want to delete users. So I have another diagram. I'm going to talk a little bit about how we maybe achieve that. So what if we said that every payload we push onto Kafka comes with an actual message, which could be a command or an event for another service, but we include with that a token and a signature. Now services have to cryptographically sign their messages. So if service A wants to send a command to service B, this is the non-corrected diagram where both of them say service A. Oh man. So that one's B. Or that one's B. Whichever you like, but one of them's A and one of them's B. But the point is that service A wants to send a message to service B, and it wants to prove that it has the authority to do so. In order to do that, it will cryptographically sign its payload, so it will generate a signature using its private key. The corresponding public key is known to service B, so service B can verify the signature. It can only have been generated by service A. We also have this token, and think about this in terms of JSON WebSockets, because that's what we actually use as it happens. And you know what, these two fields don't have to be separate, but they are in this diagram. Yes?
Service A and service A prime.
Sure.
Are the private keys the same?
Oh, no. Very good question. So, each service needs its own unique key pair. Not only that, but the keys don't live in the services. We wouldn't make these files on disk somewhere. We need some kind of secure key management system to issue these keys to the services when they are provisioned. Yes, Alex?
Such as? What tools are there?
You have KMS, for example. You have Kubernetes has its own secrets management system. So those are the only ones I'm familiar with. Yes?
How do you get the public keys distributed correctly?
Same way. So you would have it in a key management system. Now you need to trust. You have to have some trust somewhere in here. So this does
service discovery stuff.
So we don't really do any service discovery as such. What we would do is parameterize a container when it starts up. So the provisioning system talks to key management, initiates the container, and ejects these values and output. So of course you've got a runtime process, and someone who can inspect the memory of the process could get a key out of it. But if someone's able to inspect the memory of the process, you also have problems. And you should probably reissue the keys and figure out how they did that in the first place. So, yeah, but the token, it allows you to create a set of capabilities. So this comes back to the testing thing. I can say that I want to delete a user, and I have the capabilities to delete a user, which means I'm allowed to do it, and here's a cryptographic signature that proves it. If I don't actually want to delete the user, I won't set that capability flag. Say don't actually do it, don't do anything destructive. So this has the side effects of being able to be quite useful in building a chaos testing framework, which I will talk about next. A distributed system without chaos testing will fail in creative ways. What do we mean by creative? Well, software at a large scale tends to find clever ways to do things you don't expect. Almost like it's doing it deliberately. I don't have a diagram, but I do have a link to a paper. So I'll talk about chaos. So what we did is we devised a way where, given protobuf definitions, which is what we're using for encoding messages on Kafka, we can generate sample messages. So we use some heuristics here. Firstly, you've got the types from protobuf. So protobuf distinguishes types like integer and string. But we can be a little bit more clever than that. We can say, well, this field has date in it. So we'll generate ISO compatible date. A completely random one. So we have another service which we deploy, not necessarily in production, but we can. We have a service we can deploy which will generate random messages from a protobuf definition, and then we see what happens. But of course, we can configure it so that we don't do anything destructive by using the capability system that we talked about before. So yeah, we found some really interesting things. I don't actually have the screenshot that we have, but we can segfault the JVM in ways that you would not expect. Not only that, but we can create stack overflows. So this is really interesting. There's a way to craft a protobuf message, which will cause the JVM to stack overflow. And if you read that paper, you will find out how to do that. You can also do it with JSON, by the way. All right, so that's the talk. We're Disney Plus. You've probably seen it in the news recently. Disney is building a rival to Netflix. It's an on-demand video system. It's built right here in Manchester.